Hello everyone. On this video we will be looking at how to solve the derivative of an inverse function. Okay, so before we do that, we're going to kind of jump back into your, I guess you could say, pre-calc trigonometry days and look at what defines an inverse function. Okay, so an inverse function exists if, say, 1, a function is 1 to 1. Is 1 to 1. Okay, so what do we mean by a 1 to 1 function? What that means is every x value corresponds to only one y value, and that's the key there, every y value corresponds to only one x value. Okay, so the function has to be 1 to 1, and 2, the function is monotonic. The function is monotonic. Okay, and by monotonic, we just mean that it's either strictly increasing or strictly decreasing. It's not bouncing back and forth. Strictly increasing or strictly decreasing. Okay, so that's on the entire domain. Okay, so every monotonic function is 1 to 1 and has an inverse. All right, so how do we know that's true? Well, we can go ahead and prove it. Okay, so let's go ahead and prove it. Okay, so what if we assume f of x is monotonic? Okay, so what does that mean? That means it's either going all up and it's increasing for the whole graph, or it's decreasing for the whole graph. Okay, so just for the sake of this proof, because you can do the same thing for any, whether it's increasing or decreasing, we'll just do increasing. Okay, so let's say this graph here is strictly increasing. Okay, so if you have a point here, the next point of x is going to be higher, and then higher, and then higher, then higher, then higher, then higher. Okay, so it's strictly increasing. Okay, so what we're going to do is we're going to let f of x1 equal f of x2, or you can say y1 equals y2. So somewhere on that y-axis, f of x1 and f of x2 is the same point. F of x1 equals f of x2. Now let me clean that up a little bit. Okay, so f of x1 equals f of x2. Yeah, it's a little bit better. Okay. Now, if that's the case, If f of x1 equals f of x2, that means the x value for both of those has to be the same. So it has to be x1 and x2. And x1 equals x2. Okay, now what we're going to do is using the proof by contraposition. Using proof by contraposition, if x1 doesn't equal x2, so if this is not true, then the first part is not true. Then f of x1 does not equal f of x2. Alright, so now if we're looking at this proof by contraposition, we can see that just drawing a little graph to help you visualize it. So you have your x and you have your y. Let's say this is the same function here. If x1 doesn't equal x2, so let's see, this is your x1, and here they were both equal, so same spot. But x1 here does not equal x2. So that means this is your f of x1, and this is your f of x2. Okay, so if your x values aren't the same, then neither are your f of x values. Okay, so what does this tell us? That since f of x1 does not equal f of x2, this implies that either f of x1 is less than f of x2, or f of x1 is greater than f of x2. Okay, now in either case it doesn't matter. We just know that it's not equal to f of x2. So in either case, f of x1 does not equal f of x2, so f of x is a one-to-one function. All right. Okay, so if you are still writing, feel free to press pause. What we're going to give you, what I'm going to do is give you a couple of examples of what a one-to-one function would look like, because I want you to understand one-to-one functions before we get into the derivative of the one-to-one function. All right, so let's go ahead and do a couple of one-to-one examples. Okay, so let's say for this example here, we're going to draw our table. Okay, so let's say this is your x and this is your f of x. Okay, so let's say your x value is -2, -1, 0, 1, and 2. And your f of x value are 7, 9, 15, 18, and 24. All right, now with this one, this is actually a one-to-one function. Okay, how do we know that? Because if you have -2, -2 only has one x value. -1 only has one f of x value. 0 only has one f of x value. You don't see 0 appear anywhere else. So every x has only one y value. And if you look at the y values or the f of x values, you don't see 7 appear for any other x value. You don't see 9 for any other x value. You don't see 15 for any other x value. You don't see 18 for any other x value. Same thing with 24. You don't see that appear anymore for any other x value. Okay, so every x has one y value, and every y has one x value. Okay, so every x value has one y value, and every y value has one x value. Okay, let's look at the next example. Let's draw our table. We have our x, and we have our f of x. Okay, so 1, 2, 3, and 4. And again, let's go with -2, -1, 0, 1, and 2. But this time, let's go 7, 5, 4, 5, and 3. Okay, now, this table is a function, just a regular, ordinary function. Okay, why? Because every x value has only one y value. Okay, so -2 only has one y. You don't see -2 appear anywhere else with a different y value. -1, same thing. You don't see it appear anywhere else. Same thing with 0, 1, and 2. You don't see them appear anywhere else. So this is a regular function, just a function. This is a function since every x value has only one y value. Okay. Now the only thing is, it's not a one-to-one function. The one-to-one is special because for every x there's one y, and for every y there's one x. You see here, y equals 5 has two different x values. Okay, so it's just not one-to-one. Just not a one-to-one function. Okay, and that is because y equals 5. Remember, y is equal to f of x. So if you're saying, oh, where'd that y equals 5 come from? Y is equal to f of x. So that's like saying f of x is equal to 5. So y equals 5 has x equals -1 and x equals 1. Okay, so just a little note there to show you why it's not one-to-one. All right, so let's look at one more example. And again, we're going to draw our table. We have our x, and we have our f of x. And 1, 2, 3, and 4. All right, so again, let's go -2, -1, 0, 1. And instead of 2, let's put another -2 there. And make this 4, 7, 9, 15, and 8. All right, now this does not even qualify as a regular function. Why? Because x equals -2 has two different y values. Okay, so x equals -2 has two different y values. Okay, so you get the ordered pair -2, 4, and you get -2, 8. Okay, now since it's not even a regular function, it surely can't be a one-to-one function. So it's not a function. So it is not a one-to-one function. Okay, so it can't be a one-to-one function if it doesn't even qualify as a function. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next page. Excuse me. Okay, now we're going to look at the fact that if your derivative is strictly positive or strictly negative, or in other words, strictly monotonic if it's either one of those, it is one-to-one over the entire domain. All right, so let's look at a couple of examples. Okay, so what if we wanted to identify if the functions have an inverse? Okay, how do we know if they have an inverse? Because they must be one-to-one to have an inverse. Okay, so for problem A, let's say f of x is equal to x to the third power plus x minus 1. And for problem B, let's say f of x is equal to x to the third power minus x plus 1. Okay, so two different problems, just very little difference between them, just kind of switching up the signs there. That's the only difference. Okay, so how do we know if this function is one-to-one? Or how do we know if it has an inverse? We have to find out if it's one-to-one. Okay, so for problem A, we see that f of x is equal to x to the third power plus x minus 1. What does that tell us about the derivative? Well, we find the derivative f prime of x is equal to 3x squared plus 1. Okay. Now, what does this derivative tell us? No matter what x value we plug in, and the fact that this is a plus 1, this will always be positive. The derivative, no matter what, you can try any x value you want. That's a real number. We're not talking like complex numbers. We're only dealing in real numbers. If you plug in any x value, your derivative will always be positive. Okay? Which leaves us right up here. If your derivative is strictly positive, or over the entire domain, then it's monotonic, so that means it has an inverse. Okay? So again, if you want to, go ahead and plug in various positive, negative, zero, doesn't matter. It'll always be positive. Okay? Since f prime of x is positive for every real x value, that's the key, real. And all that means is that the slope is positive. the function is monotonic and has an inverse. Okay. Now the same thing would be true if your derivative was always negative for no matter what x value you plugged in. So it doesn't have to always be positive. If it's always negative, no matter what x value you plugged in, then it would be the same thing. Okay, so if we wanted to sketch just kind of a makeshift graph of x to the third plus x minus 1, it will look kind of like this. So you have your x and you have your y. It would look somewhat, not exactly, but if you want to plug it into your graphing calculator, take a look at it, you can. It will look something like that, which means that the slope, no matter what point, would always be increasing. Okay, so those are all of your tangent lines on that graph. No matter what point you pick, the slope would be increasing. It may increase just a little, or it may increase a lot, but it's always increasing. Okay, so that's how you know this has an inverse that actually does exist. All right, so let's move on to B. And move that up a little bit. There we go. Okay. So for B, let's say f of x is equal to x to the third minus x plus 1. Okay, if we find the derivative of that, we find f prime of x is equal to 3x squared minus 1. Okay. Now, if you see here, there are actually some values of x that will make this positive, and there are some values of x that will make this negative. So when x is equal to 0, okay, so when x is equal to 0, what does that give us? F prime of 0 is equal to 3 times 0 squared minus 1, which is negative 1. But when x is equal to negative 1, our derivative at negative 1 is equal to 3 times negative 1 squared minus 1, which is positive 2. Okay, so you can see here, you have a negative slope and a positive slope. Okay? So if that's the case, you can see it's not monotonic. Okay? So since you have both positive and negative slopes over the domain, the function is not monotonic. Okay, which means that there's no inverse. Inverse doesn't exist. All right. So if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page. Okay, and this will instruct you on how to find the inverse function equation. Okay. And again, if you remember this from pre-calc or trig, you're ahead of the game. This is just more of a reminder than anything. Okay. So 1, we want to find out, just like we did before, is it 1 to 1? See, f prime of x is strictly increasing or strictly decreasing. Okay, once you find out that's the case, 2, you replace f of x with y. Okay. Now your third step, you interchange all x's. Let me clean that up a little bit. And y's. Okay, that means you change your x to y's and your y's to x's. Your fourth step, you solve for y, and then your y will become f inverse of x. Okay, so 2 little notes you want to make sure you're aware of. That the domain of f of x becomes the range of your inverse, of f inverse of x. Okay, now you can always double check your answer. And if you don't remember, this is how you would do it. You can always check your answer. Because if you take the function of the inverse, that should equal x. Or if you take the inverse of the function, it should give you your x. Okay, so you can always double check your answer. All right. So if you're still writing, feel free to press pause. But we're going to go ahead and do a quick example of this one. Okay, so what if we wanted to find the inverse of f of x equals the square root of 2x minus 3? All right. So we know that f of x, we can actually rewrite that to be 2x minus 3 to the 1/2 power. Okay, which means our derivative prime of x is going to be 1/2 times 2x minus 3, and we subtract 1 from there, so we have negative 1/2 times the derivative of what's inside, or of our 2x minus 3. Okay, so that means our derivative is equal to 1/2 times 2x minus 3 to the negative 1/2 power. Derivative of 2x minus 3 is just 2. All right. So of course this 2 and the 1/2 cancels out. So you have 2x minus 3 to the negative 1/2 power, or your derivative is equal to 1 over the square root of 2x minus 3. All right. So what does this tell us? Well, this tells us the domain. We know that the denominator can't equal 0, and it can't be negative, because once you get into negative square roots, you're no longer in real numbers. So we know that 2x minus 3 has to be greater than or equal, well, actually just greater than 0. Okay, so that means if you solve for x, that means x has to be greater than 3 over 2. Well, actually, for this one, it can be greater than or equal to, because you're a function of x. But we'll get into that later. Okay, so that means it can be 3 over 2 all the way to infinity. All right, so we go to our second step. Well, might as well mix the second and third step. So this is our first step. So we mix our second and third step. We have f of x equals the square root of 2x minus 3. It's the same as saying y is equal to the square root of 2x minus 3. Okay, so now we interchange our x and y. So instead of y is equal to that, we make that x is equal to the square root of 2y minus 3. Okay, so all we did was swap our x and y. Okay, so if we square both sides, that's x squared equals 2y minus 3. We add 3 to both sides, we have x squared plus 3 equals 2y. Divide everything by 2. That gives us y equals x squared plus 3 divided by 2. Okay? So that brings us to our fourth step. Well, I guess you could say it's our fourth step. Which means we change that y to f inverse of x, which is x squared plus 3 over 2. Okay, so this is your inverse of f of x. As long as it's over the proper domain. Okay, it's not for every real number, but just for the domain. Okay, now how do you check to make sure it's true? This is how you check it. You take the function of the inverse, okay, so you have f of x So let's see, the best way to do this, let's say f of f inverse of x also equals x. Okay, so that's equal to f of, what's your f inverse? X squared plus 3 over 2. So f of x squared plus 3 over 2. So that's your function of your inverse. Okay, now what does this tell us? Well, since we know that f of x equals square root of 2x minus 3, we just replace the x with x squared plus 3 over 2. Okay, so that's square root of 2 times x squared plus 3 over 2 minus 3. Okay, so you can see here the two squares cancel, well, the 2's cancel each other out. So you have x squared plus 3 minus 3. Where those two cancel each other out. So you have square root of x squared, which is equal to x. So that's how you know that is the proper inverse. Alright, so if you are still writing, feel free to press pause. But now we're going to look at the derivative of an inverse function, okay, which will make all of these things that we just went over a little bit more relevant. Okay, so let's say if f of x has an inverse function. F inverse of x. Okay, now if that's the case, then the derivative of f inverse is equal to 1 over f prime of f inverse of x. All right. So we're going to go ahead and prove that that's the case. Okay. So what if we let y equals f of x? Okay. So what if we know like the exact value of x? So if we can plug in some value of x, then that means that y sub 0 will equal some f at the value x sub 0. Okay, so we're going to just start off with these two. So we have our y equals f of x. Our y sub 0 equals f of x sub 0. So now we just have to find the inverse. Okay, so if we apply f inverse to both sides, so we have f inverse of y equals f inverse of f of x. Okay, so we know that f inverse of f of x, those two kind of cancel out, which leaves us with just x. That means f inverse of y is equal to x. Okay, but at a specific x and y value, it also means f inverse of y sub 0 is equal x sub 0. Okay, so those four little equations kind of help us along with our proof. Okay, how do we prove most derivatives? Well, the limit definition. So you have the limit as y approaches y sub 0, f inverse of y minus f inverse y sub 0 all over y minus y0. Okay, so that equals the limit as y approaches y sub 0. Remember, your y is equal to f of x. So f inverse of y becomes f inverse of f of x. Minus f inverse of y sub 0 becomes f inverse of f of x sub 0. Inverse of f of x sub 0. All over y minus y0, so y is equal to f of x. So that'll be f of x minus y sub 0, which is f of x sub 0. All right. So let me move this up a little bit. So we have our limit, and we see here f inverse of a function. Those two kind of cancel out, so you're just left with x. So x minus f inverse of a function, so x minus x of 0 all over f of x minus f of x of 0. But in this case, is as your x approaches x of 0. Because if x is equal to x of 0, you just have 0 in your denominator, which you can't have. Alright? So now, if you kind of think a little bit back, you see that the limit as x approaches x0, this is just kind of a side note, so this isn't part of the proof, is equal to f of x minus f of x of 0 all over x minus x0. That's equal to f prime of x0. Or you can make it f prime of x0 over 1. Same thing. Oh, x minus x0. There we go. Okay. Why is that important? Because if you look at where we are now in our proof, it's the reciprocal of our limit definition. Okay. So since this is just the reciprocal of our limit definition, we have the reciprocal of our derivative. So that's equal to 1 over f prime x of 0. Which in this case, what is our x of 0? That's 1 over f prime, let's move that up a little bit, of f inverse y sub 0. Alright? Well, that's of course if we have a specific value. Alright, so if you are still writing, feel free to press pause. But we're going to go ahead and we're going to go ahead and move on to our example. Okay, so what if we wanted to find f inverse prime at -7 when f of x is equal to 3x to the third plus x squared plus x minus 12. All right, and let's say we are given that f of 1 is equal to -7. All right, so to solve this one, we know that our f of 1 is equal to -7. That's our given. Okay, so what we have to do now is find the inverse. So if we apply f inverse to both sides, you have f inverse of f of 1 is equal to f inverse of -7. So since those two will kind of cancel each other out, you see that f inverse -7 is equal to 1. All right. So now going back to our formula, f inverse prime x is equal to 1 over f prime of f inverse, make that look more like an inverse, f inverse of x. Okay, here, that means it's 1 over f prime. We already know our x is -7, so that's f inverse at -7. Okay, but cool thing about this is we know what f inverse of -7 is. It's 1. So f inverse prime of x is equal to 1 over f prime of 1. Okay, so what do we have to do here? Easy. We just still have to find f prime of 1. Okay, so that means our f of x is equal to 3x to the third plus x squared plus x minus 12. Then your derivative, f prime of x, is equal to, bring down that 3, so you have 9x squared plus 2x plus 1. Strictly monotonic, it's increasing, so you're good. Okay, so f prime of 1 is equal to 9 times 1 squared plus 2 times 1 plus 1. So f prime of 1 is equal to 12. So that means your f inverse prime at -7, which is equal to 1 over f prime of 1, is just equal to 1 over 12. All right. So if you are still writing, feel free to press pause. We're going to go ahead and move on to our next example. Okay. So what if we want to find t inverse prime at -8 when t of x is equal to -x to the third minus 8x minus 8. And that's given that t at 0 is equal to -8. Okay. Now what I want you to do, go ahead and press pause and use the same process for the previous example to solve this one. Alright, so assuming that you've pressed pause and worked this one out, let's go ahead and verify your answer. Okay, so we know that t at 0 is equal to -8. We take the inverse to both of those. If t inverse at t of 0 is equal to t inverse -8. Of course, these two kind of cancel each other out, which means that t inverse at -8 is equal to 0. Alright, so we're going to, of course, need that. Okay, so if we plug in our formula where t inverse prime at x is equal to 1 over t prime of t inverse of x. Okay, now in this case, our x is equal to -8. So that means our t inverse prime at -8 is equal to 1 over t prime times t inverse at -8. Okay, luckily enough, we know that our t inverse at -8 is equal to 0. So that means it's going to be 1 over t prime 0. Once we replace that with 0. Okay, so what do we have to do? Same thing as before. We have to find our t prime of 0. Okay, so we know that our t of x is equal to -x to the third minus 8x minus 8. So our t prime of x is equal to -3x squared minus 8. Derivative of -8x is 8. Derivative of that one is just 0, so it disappears. Okay, so t prime 0 is equal to -3 times 0 squared minus 8. So t prime 0 is equal to -8. So that means our t inverse prime at -8 is equal to 1 over t prime 0, which is -1 over 8. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. Excuse me. All right. So let's say that given that y of x is equal to 5x plus 2 over -2x plus 1, want to find y inverse prime at -3. Okay, and note that y of 5 is equal to -3. Okay, now if you're ever not giving the note part right here where you have a specific point, you can always solve it. So if you have y inverse prime at -3, then what you want to do is you want to solve this for -3 and say, okay, 5x plus 2 over -2x plus 1 equals -3 and solve for x. Okay, so you know y of some value will give you -3. Okay, so this is sometimes, most of the time it's given to you and sometimes it's not. So sometimes you would have to find that on your own. Okay, so to solve this one, you know that y of 5 is equal to -3. Apply y inverse to both sides. So y inverse of y of 5 is equal to y inverse of -3. Where those two kind of cancel each other out. Okay, so you have y inverse and -3 equals 5. Okay, so that means that your y inverse prime at -3 is equal to, let me kind of separate that so it's not too close, 1 over y prime at y inverse at -3. Okay, so we know y inverse at -3 is equal to 5, so that's just going to equal 1 over y prime of 5. So just like before, we find y prime of 5. Alright, now this one, a little more work because you have to use the quotient rule. So y of x is equal to 5x plus 2 over negative 2x plus 1. Now y prime of x, move that up a little bit, is equal to the denominator, negative 2x plus 1, times the derivative of the numerator minus the numerator times the derivative of the denominator all over your denominator squared. Negative 2x plus 1. Squared. Alright, so that will give us negative 2x plus 1 times the derivative of 5x plus 2 is just 5 minus 5x plus 2 times the derivative of negative 2x plus 1 is just negative 2. Again, all over your denominator squared. So if we distribute that 5 and distribute that negative 2, we will end up with negative 10x plus 5 plus 10x plus 4 all over negative 2x plus 1 squared. Where these two cancel each other out. So that leaves us with our derivative of 5 plus 4, which is 9, over negative 2x plus 1 squared. Alright. Now, since we want to find y prime of 5, so y prime of 5 is equal to 9 over negative 2 times 5 plus 1 squared, which is 9 over 81. Oops. Okay, so that means your y prime at 5, oh, sorry about that, is 9 over 81, which simplifies to 1/9. And I'll draw a little circle around that since we're going to be using it. So that means that our y inverse prime at negative 3, which is 1 over y prime of 5, is equal to 1 over 1/9, which is just equal to 9. Alright, so if you are still writing, feel free to press pause. Okay, so we're going to go ahead and move on to our next example. Alright, so let's say, for example, we want to find h inverse prime at positive 7. At positive 7, given that h of x equals the square root of 10x plus 9. Okay, and again, if they didn't give you this part, you can always figure it out by finding which value makes that equal to 7. So note that h of 4 is equal to 7. Alright, so what I want you to do is go ahead and press pause and try to work this one out on your own. Alright, so I'm assuming you've already worked this one out, so let's go ahead and verify your answer. Okay, so we know that h of 4 is equal to 7. So if we apply h inverse to both sides, where those two kind of cancel each other out, we know that h inverse at 7 is equal to 4. Okay, so using our formula, h inverse prime at 7, we know that's equal to 1 over h prime at h inverse of 7. Okay, if you know h inverse at 7 is equal to 4, so that's just, clean that up a little bit, equal to 1 over h prime of 4 at 4. Okay, so just like before, we find our h prime at 4. Alright, so kind of separate that a little bit. You know that h of x is equal to square root of 10x plus 9, but we're going to rewrite it as 10x plus 9 to the 1/2 power. So if we find the derivative, that's going to equal, bring down the 1/2. 1/2 times 10x plus 9, subtract 1 from that, is negative 1/2 times the derivative of what's inside. Okay, so that's going to equal 1/2 times 10x plus 9 to the negative 1/2 times the derivative of 10x plus 9, which is just 10. Okay, so if we go ahead and combine the 1/2 and the 10, we know our h prime of x is equal to 5 times 10x plus 9 to the negative 1/2, or 5 over the square root of 10x plus 9. Now at x equals 4, you have 5 over the square root of 10 times 4 plus 9. Okay, which ends up being 5 over the square root of 49. So your h prime at 4 is equal to 5 over 7. Alright, so to kind of help us finish it off, you know, our h inverse prime at 7 is equal to 1 over h prime 4, which is equal to 1 over 5 over 7, which is equal to 7 over 5. Alright, so that's how you find the derivative of an inverse function. Alright, hopefully this made sense, and I will see you on the next video.